Today let's talk about 2012 AMC 10A Problem 18. The closed curve in the figure is made up of 9 congruent circular arcs, each of length 2 pi over 3. So, before we continue to read the problem, what arcs are we referring to? Well, we're referring to these ones. 1, 2, 2, 3, 4, 5, 6, 7, 8, 9. So those arcs have a length of 2 pi over 3, where each of the centers of the corresponding circles is among the vertices of a regular hexagon of side 2. Let's draw the hexagon. Basically, it means if you connect the centers of the circles of the arcs, you get the hexagon with side length 2. We just connect the side length. I'm zooming in so the sides are straighter. So like that, right? So we connect the centers of the arcs presented. And then, basically, the question says, what is the area of the enclosed curve? So essentially, what is the area of this, the fidget shape like thing we're looking at, the fidget spinner thing. So this area here. So essentially, we want to use the regular hexagon because the regular hexagon has to have some help, or else they wouldn't tell you to draw it, right? Well, it does have some help because we can first figure out areas outside of the hexagon, like this one, and the other 2 areas like that. The 3 blue areas are actually congruent. And then we can figure out the area inside the hexagon. We can figure out the area of the hexagon. Just like figure out the area of the hexagon. And then you subtract that area that you figured out. You subtract that area from these 3 green sectors that are congruent. Like this. You subtract that yellow area with the area of the hexagon from the 3 green sectors, and then you sum the resulting areas up, and you get whatever you want. So let's just figure out the blue sectors first. For the blue sectors, you only have to figure out one area, right? And then you multiply that by 3. So we want to figure out this angle, the central angle. And then, so how do you figure that out? Well, essentially you realize that, so this arc is 2 pi over 3. This arc is also 2 pi over 3. So the total arc length is actually 4 pi over 3. If we have the circumference, then we can figure out. If we have the circumference, then we can figure out our whole circle, like our angle. So what's the circumference? Well, it says the regular hexagon has side length 2. And since we have 9 congruent circular arcs, it means that these 2 sides are the same. So the radius of the circles are the same. So this is 1 and this is 1. So we have radius of 1, so the diameter is going to be 2 pi r, so 2 pi r, which is just 2 pi. If the diameter is 2 pi, then the blue area is 4 pi over 3 times 1 over 2 pi, which is 2 over 3 of the area of the whole circle. So we can figure out the blue area. That's just 2 over 3 times pi r squared, which is just 2 over 3 pi. So then the blue area in total is going to be 3 times 2 over 3 pi, which is just 2 pi. What about the area of the hexagon? We can split that into a few parts. Okay, so one part is this. One part is the triangle on top. Another part is the rectangle in the middle, and the third part is the triangle at the bottom. Okay, so we begin with trying to find the base of the triangle and the height of the triangle. So essentially we can use, so how do we find the base of the triangle? Well, the base of the triangle is, actually we can't find the base of the triangle right now, okay. But we know the hypotenuse is 2, right? We know that the hypotenuse is 2. And maybe we can use that fact because this kind of looks like a 30, 60, 90 right triangle. So let's just prove that it is a 30, 60, 90 triangle. Well, first we can use this angle here, because that's just the interior angle of a regular hexagon. The interior angle of a regular hexagon is 180 degrees times 4 over 6, which is 180 degrees times 2 over 3, which is 120 degrees. So this is 120, and this should be a right angle because we've made the part in the middle a rectangle. Therefore, this part is actually 30 degrees. Therefore, this angle is 60 degrees. So we have a 30, 60, 90 triangle indeed. And these two triangles are congruent. So we don't have to figure out the other triangle. We only have to figure out one part of the triangle. So this is 30, 60, 90. So if this hypotenuse is 2, the side opposite to the angle of 30 degrees is going to be 1. Therefore, this side here opposite to this angle of 60 degrees is going to be root 3. So the area is just going to be, so the area is root 3 times 1. So 2 times, so the area of the one small right triangle is root 3 times 1 times 1/2, which is just root 3 over 2. We have 4 of these small triangles like this, right? We have 1, 2, 3, 4. So we have 4 times root 3 over 2, which is just 2 root 3. And then we want to figure out, so we already have the length of this triangle, this rectangle, because it's just 2 root 3. But we want the height. So we want the width of this rectangle. So what is that? Well, that's just 2, because it says the side length of a regular hexagon is 2, and this is the side length of the regular hexagon. So that's just 2. So we have 2 times 2 root 3, which is equal to 4 root 3. So the area of the hexagon is 6 root 3, because if you sum these two up, that's 6 root 3. So we want to minus that by the area of these green circle sectors. So you minus 6 root 3 minus 3 times the area of one green sector, which is, Okay, so we are given that this arc length here is actually 2 pi over 3. And we know that the radius is 1. This means that this angle here is 120 degrees. And we also know this because this is the interior angle of a regular hexagon. So this is 120 degrees. So that is 1/3 of the area of an actual circle of radius 1. So 1/3 pi r squared, or 1/3 pi 1 squared. So just 1/3 pi. So that's equal to 6 root 3 minus pi. Finally, if you add the blue and the yellow area together, you get 2 pi. You get 2 pi plus 6 root 3 minus pi, which is equal to 6 root 3 plus pi. The answer here is E. So thanks for watching. Remember to like, subscribe, and share. The key point here is to use the hexagon to its maximum utility. Thanks for watching. Bye.